Hello everyone. I guess it's already 3:02 and we should start our session. So this is our fifth live session and the course is being taught by Professor Sanjeev Samani. And let's start today's session. So let's begin solving problem number 1. It says that this is related to the scattering. So in here we are having three scattering mechanisms present in a particular semiconductor, and we have been given conditions that if only first scattering mechanism was present, then the mobility would have been 200 centimeter square per volt second, and if only second mechanism was present, then the mobility would have been 1500 centimeter square per volt second. Similarly, if third mechanism would have been present, then the mobility would have been just 500 centimeter square per volt second. So now what we have been told to find out the net mobility. Net mobility will be the less than the least value. Okay, we know that all these scattering mechanisms will now effectively work for our system, for our semiconductor system, and the net mobility will be given by the Mathiassen's rule. Okay, so the net mobility will be given by the Mathiassen's rule. And it will be the combination of these individual mobilities, 1 by mu 1 plus 1 by mu 2 plus 1 by mu 3. Okay, now they are all scattering mechanisms that are present in our system. So it will be simple enough. 1 by first mobility is 2000 plus 1 by 1500 plus 1 by 500, or simply okay, we are just simplifying this thing. And now if I take the inverse, which will be my net mobility, it will simply be 500 in 12 divided by 90. So let's calculate this value. So it comes out to be equal to 315.7. Okay, and the units will be centimeter square per volt second. So this is the option we have got. So from this you can clearly see option A is the closest. So we will select option A for this problem. Now moving to another problem. It says that we have a semiconductor which is in thermal equilibrium. Okay, so by thermal equilibrium, it has been given over here that we are having in the thermal equilibrium, we will be having no external, or we can say, agent acting on the system apart from the temperature. Okay, temperature is the only external agent that is acting on our semiconductor system, and as a result of this thing, we are having no current in the semiconductor. Okay, because of the semiconductor being in thermal equilibrium. And also we have been given the donor concentration, and the donor concentration varies exponentially with distance distance x. Okay, x, where x is between 0 to zero point 0.1 meters. Okay, and L naught is the constant, so it's a decaying function. And from this you can clearly see that this concentration, electronic concentration, will be decreasing. So now we have been told to find the value of the electric field. Can you just comment, if you want, how this electric field will be generated? Okay, so since in this system we are having the concentration gradient, because as you can clearly see, the concentration at x equal to 0, let's say, it will be nd of 0, and it will be simply n naught. Similarly, at x equal to zero point 0.1, it will be nd at x equal to zero point 0.1 meters is equal to n naught exponential of minus 10 into zero point 0.1, which is simply n naught exponential of minus 1. This clearly indicates that there is a concentration gradient, and as a result of this concentration gradient, we will be having the diffusion current. And because the system is in thermal equilibrium, we will be having an electric field that is generated in this region where we have this concentration gradient, and this electric field will counterbalance the diffusion current that is being generated because of this, what we can say, because of this concentration gradient. So the electric field is the inbuilt electric field, similar to the case of what you have seen in PN junction or metal semiconductor junction. Whenever there is this concentration gradient, when for example we are connecting P material and N material, there will be the gradient that will be occurring at the interface, not only at the interface, close to the interface. Because of that gradient, the carriers will move from P to N and N to P. Holes will move from P to N and electrons will move from N to P. And you have seen how that region, which is now having some immobilized ions because of this uncovering of the charges, or the movement of the charges, the carriers from the p side to the n side, and from the n side to the p side. So the this results in the built-in field, which you must have seen to be equal to the built-in potential in the calculations whenever you are doing PN junction or metal semiconductor junction. Okay, you have seen that thing. So this is a similar kind of a concept. Because of this concentration gradient, now we will be having this built-in field. Okay, so in total, because there is no current, and current in total is combination of two things. Okay, one is the drift and another is the diffusion. If I simply multiply this by area, so this is the current density what I have written. So current, total current is the diffusion current plus the drift current. It's as simple as it gets. But since we are in thermal equilibrium, the total current will be, we will be having no current throughout, through. For example, if we connect, uh, uh, if you try to measure the current for this, you will be getting no current in the system because it is. But there is a scenario for this. If I try to measure something, for example, if I am trying to measure current, I will be applying some voltage to it that will disturb my thermal equilibrium. So I cannot measure that. Okay, so that's why it has been always told to us, and we always see in the books that this built-in potential cannot be measured, because whenever we go for the measurements, we have to apply the external bias, and as a result of that thing, we have, whenever we are applying some external agent or external force on the system, what is happening is simply we are disturbing the thermal equilibrium. Okay, so we are not in thermal equilibrium at that time, and as a result we cannot measure that built-in potential. Okay, so similar is the case over here. So the total current is now, since it is in thermal equilibrium, we are having zero current. Okay, so we can write I total to be equal to zero, and drift current is simply due to the electric field, where now this mu n is the mobility of the electrons, because we know this donor concentration has been given to us, and as a result of this thing we can clearly say that this is n type. Okay, donor belongs to n type, so it is q times mu n times the concentration of the electrons times the field. Oh, this will be the field generated. Okay, plus q times, now this is the diffusion coefficient will come over here, because this is the diffusion current we are looking into, dN by dx. This is now due to the concentration gradient. Okay, this is due to the concentration gradient, this component. So from this we have to find out this electric field. What is this value? Now we know the value of q, we know the value of n, we know the expression for n. So let's first find this dN by dx. Okay, and let's try to calculate it first. So d, so n is, it is 0 is simply equal to q times mu n. N was n naught exponential of minus 10x, n naught exponential of minus 10x times the field, plus q dn. Okay, dn by dx is simply d by dx of n naught exponential of minus 10x. So since this is equal to 0, q we can drop now. It is simply mu n, n naught exponential of minus 10x times the field plus dn times n naught exponential of minus 10x times minus 10. Okay, this whole thing is equal to 0. So now this n naught and exponential of minus 10, it can be taken out to be equal to, it can be taken out of the whole expression, and this whole thing cannot be 0 because n naught is, let me write it explicitly, exponential of minus 10x times n naught is simply mu n times e minus dn times 10. Okay, is equal to 0, but this cannot be 0 because n naught is constant and exponential of minus, let's say, since this is between 0 to 1, it is always having some finite value, so this cannot be 0, and only thing that can be equal to 0 is mu n dn. Mu n e minus dn is simply, this is the expression is equal to 0, or simply the electric field is simply 10 times dn by mu n. Okay, you you must have seen the Einstein's relation. Okay, the Einstein's relation says that the ratio of this diffusion coefficient and the mobility, okay, is simply dn by mu n is simply kt by q. Okay, and at 300 Kelvin, simply this dn by mu n will simply be equal to 26. Okay, now from this you can clearly see this value of electric field will come out to be equal to 10 times 0.026, or electric field is simply 0.26. So we have got the value, and option C is matching our results. We have taken the the temperature also to be equal to 300 Kelvin, which was given in the problem itself. Okay, now moving to another problem, which says that we have a semiconductor, and this sample of semiconductor, it has some cross sectional area which is equal to 1 centimeter square, and the thickness is zero point 0.1 centimeter. Okay, what we have to do now is we have to find the number of electron hole pairs that are generated per unit volume. Okay, so number of electron hole pairs that are generated per unit volume per unit time by the absorption of some light. So we are having some light external source, and as a result of that thing we will be having the absorption of the carriers. So let us first understand. Also, we have been given that each photon creates one electron hole pair. So that's what we need first. So number of photons will be number of electron hole pairs that will be generated in this semiconductor bar. So it will simply be, this system semiconductor bar is having area of 1 centimeter square and thickness is 0.1 centimeter. Okay, so the number of electron whole pairs is simply equal to number of photons created. So the power is given to be equal to 1 watt. Okay. Also the wavelength of this light is given to be equal to 6300 angstroms, which is 6.3 into 10 to the power of minus 7 meters. Okay. Yes, it's correct, because 1 angstrom is 10 to the power of minus 10 meter. Okay. So from this we can say that we can find out the energy of one photon, which will be given by the wavelength is equal to, sorry, E is equal to h nu. And since we know the wavelength, with this is simply the Planck's constant, 6.626 into 10 to the power of minus 34 into c is the speed of the light. This will be in meter per second. 3 into 10 to the power of 8, 6.3 into 10 to the power of minus 7. Meter and meter will go, and the energy will simply be, let's calculate this value. So it is simply 6.626 into 3, 6.3, which is 3.15 into 10 to the power of minus 19 joule. 3.15 into 10 to the power of minus 7 joule. Okay, this is the value of the energy of one photon. Now energy applied per second. So since this power is energy per second, we can clearly say that energy applied per second is uh, 1 joule. Okay, because 1 watt is the power. Okay, so we can say, you can clearly say that energy, because power was 1 watt, energy applied per second is 1 joule. Okay, because power is energy per second. Okay, so the number of photons generated will simply be let's be clear, generated per second, because we have this energy which is per second, energy applied. Okay, is simply now the 1 joule is the total energy that's applied, and energy associated with one photon, which we found out to be equal to 3.15 into 10 to the power of minus 17, sorry, minus 17 or minus 19. It is, sorry, it should have been minus 19, because it is going up, and it is 10 to the power of minus 19 over here. Sorry. Okay, so it is 3.15 into 10 to the power of minus 19. This is the number of photons that will be generated, because we have applied 1 watt of power source, and the wavelength associated with the light was 6300 angstroms, and as a result we are having this much number of photons times the energy associated with one photon should be equal to 1 joule, and as a result of this thing we are getting the number of photons. Okay, so this is the number of photons which is associated with number of electrons, electron hole pairs. So this comes out to be equal to 3.17 into 10 to the power of 18 photons per second. Okay, so we have to find the number of electron hole pairs per unit volume per unit time. Okay, so for volume, now for this thing we need to find out the volume first, because we have to find it per unit volume in the units of per unit volume as well. So the area is 1 centimeter square and it is 0.1 centimeter the thickness. So in total we'll be having the volume to be equal to zero point 0.1 centimeter square. So number of electron hole pair generated per unit volume per unit time. So the electron hole pairs generated per second per unit volume of semiconductor is simply 3.17 into 10 to the power of 18 divided by 0.1. It is 3.17 into 10 to the power of 19 EHPs. Okay, electron hole pairs per volume per second. Okay, the second. So option A is matching, so we will be selecting this option since it is matching with our answer. Okay, so now let's move to another problem. It says that we are having an intrinsic silicon, and now this intrinsic silicon is doped with arsenic atoms. Since it is doped with arsenic atoms, we can say that since this is arsenic is a pentavalent, we can say that it is a donor. It will act as a donor impurity, thereby giving the system an extra free electron. Okay, and the uh, donor sites will now be immobile sites, and they will be having the positive charge. And as a result of the if we see the semiconductor as a whole, it will be still charge neutral, because Nd positive is what has produced the free electron. Okay, so overall the system will be charge neutral. So now this intrinsic silicon wafer is doped to the concentration of 10 to the power of 16, okay, per centimeter cube. And now a small amplitude low frequency AC voltage signal is applied, which is V in, across this doped silicon. Okay, and a current of I in flows through this. Now we have to assume this block to be cubic, with each side to be equal to 10 micrometer, and we have to assume that the ionization is complete, that all the dopant atoms are ionized. And as a result of this thing, we need to find the dynamic resistance of this block, which is dV I in by di in, which is simply the resistance of this block. This is dynamic resistance of this block. And the intrinsic carrier concentration is given to be equal to 10 to the power of 10, and mobility is given to be equal to 1000 centimeter square per volt second for electrons, and it is 350 for centimeter square per volt second for holes. Okay, let's see what we can do with these numbers. First of all, we are having the donor impurity, Nd is equal to 10 to the power of 60 per centimeter cube. This is the first thing we have. From this we can find the whole concentration, which is simply in thermal equilibrium Ni square by N. Nd is approximately N is approximately equal to Nd, so it will be simply 10 to the power of 10 whole squared divided by 10 to the power of 16. It is 10 to the power of 4 per centimeter. This is the whole concentration. Okay, now this dV in by di in, it is the dynamic resistance of this block. Okay, so it's the dynamic resistance of this block, and it will simply be equal to now R, which is simply rho L by A. Since this is a cube, each side is equal to L. This will be area will be simply L square. This L and L will go. We will be left with rho by L. Okay. Now we need to find the value for this rho. Rho is simply 1 by q n mu n plus p mu p. Okay. But we can approximately say that this whole expression is simply equal to q n mu n, as concentration of electrons is much greater than holes, and also the whole mobility is less, but that's not that much less, can say, because considering the mathematical notion only, because it's just 350 and the other is 1000, but the value of P, which is the whole concentration, it is much less compared to the Nd. So we can clearly neglect this, because it will be 10 to the power of 4 and other is of the order of 10 to the power of 16. So there is 10 to the power of 12 order difference. Okay, there is 12 orders of difference between these two. Okay, so you can say now this dvi in by di in is now simply 1 by rho into, sorry, rho by L, which is rho by L, and rho is nq mu n, and L is simply L. So it is 1.6 into 10 to the power of 19, which is the electronic charge, times n is 10 to the power of 16. Okay, mobility is 10 to the power of 3, and L is simply, okay, it is 10 micrometer, or if I convert it into centimeter, it will be 10 into 10 to the power of minus 4 centimeter. Okay, so it will be 10 into 10 to the power of minus 4 centimeter, because we are dealing in centimeters, because the value of this electron concentration, what we took, it was in per centimeter cube. Similarly, the mobility was in centimeter square per volt second. As a result of this thing, L has to be taken in the units of centimeter only. So it is simply if we now solve for this, we just simply 1.6 as it is 10 to the power of minus 3, it is 3, it is 10 to the power of 3, it is 10 to the power of 3 divided by 1.6, it is 0.625 kilo ohms, 0.625 kilo ohms. So none of the option is matching, so we will go with none of these for this problem. Now moving to another problem which is associated with the location of the traps in the band gap. So before doing this, let me have some water. So it says that we have to find the location of the traps inside the band gap that will produce the most efficient trap assisted recombination, and we have to assume the degeneracy factor of the trap is 1 and the minority carrier lifetimes for both electrons and holes is both the times are equal. Okay, so let's go to the simply the recombination rate formula which we saw in the which professor taught us in the class. So let us look into that first and let us see how we can have this efficient trap assisted recombination in a material. So in steady state, recombination rate is given by simply R is Np, where N and P are the electron and hole concentrations, Ni square is the intrinsic carrier concentration, N plus N1 times the tau P, P plus P1 times the tau N. Now this trap and electronic uh, the carrier lifetimes and the concentration associated with the traps will now be given by simply N1 is simply given by Ni is the intrinsic carrier concentration, Gt is the degeneracy factor, exponential of Et, where Et is the trap state energy, minus Ei IKT. So this is the trap state location what we need to find out. Similarly, P1 is simply Ni by Gt exponential of Ei, sorry, not minus, exponential of Ei minus Et by Kt. Okay, so we need to maximize this expression, this equation 1 with respect to the trap energy level. So what we need to do is we need to find out this dr by det equal to 0. Okay, we need to find out this thing. So let us use these expressions for dr by det is simply equal to np minus ni square times the if I use UV rule of differentiation, since it is u of the form of u by v, we can clearly say that this is simply tau p times Tn1. What I have done, I have differentiated this equation. I have differentiated this equation 1. Let me write it down over here. Differentiating equation 1 with respect to Et. That is what has been done above. Okay, that's what we have done. Plus tau n dp1 by det. This whole thing is multiplied by minus 1 because it was we have used UV rule, and the differentiation of this thing with respect to Et was 0, so it was simply this was 0 minus of differentiation of dV with respect to Et, considering this np minus ni square to be equal to u, and in denominator we have considered v to be equal to n plus n1 times tau p plus p plus p1 times tau. Okay, this is after using the u by v form. Okay, so this is minus dv by det by v square. So the v square is simply now n plus n1 tau p plus p plus p1 tau n whole square. Okay, let me encircle this thing in red so that we don't get confused. Okay, so from this, since this has to be equal to 0, but n p is not equal to ni square because we are in non-equilibrium condition. In non-equilibrium condition, wait a second. Where would he previously appear? I don't know actually. I do not have access to the previous year papers, so I cannot comment on this. You can ask this similar thing in the forum because I do not have access to the previous year papers and I do not know where to find them. So I cannot comment on this. I do not know. Okay, you can ask in the forum. Like if no one is able to answer, then what you can say, you can solve the problems from the various books, device physics books. That's what you can do. I cannot comment on this. Sorry, I do not know actually, so I cannot comment on this. Where you can find the previous year papers. So this np cannot be equal to ni square. So this thing np minus ni square, it is not equal to 0, and the denominator, and from this you can see that denominator cannot be equal to itself 0. So the only thing that can be equal to 0 is this tau p times dn1 by det plus tau n dp1 by det. This thing can be equal to 0. from this expression, what you can see over here. Because we are in non-equilibrium condition, Np cannot be equal to Ni square. We will be having some delta N and delta P associated with the total electron and hole concentration itself. So now we have the both the N and P concentrations, and dN, the derivative of N1 with respect to Et will simply give me N1 is simply Nigt Et minus Ei by Kt. So it is simply Nigt by Kt. This Kt came from the differentiation. Once we differentiated this thing, it is Et minus Ei by Kt. This whole thing is simply Ni. Okay, so it is simply Ni by Kt. This dN1 by det. dP1 by det is simply, it is Ni by Gt, Ei minus Et by Kt. So it is simply minus 1 by Kt, which came after the differentiation. Okay, and this thing is simply Ni by Gt exponential of Ei minus Et by Kt. This whole thing is equal to Pi. So it is minus P1, not Ni, it is N1. So it is N1. So it is P1 by Kt. Okay. So let us use these. Let us use dN1, det, and dP1, det in equation 2. Okay, so it is simply, tau p times N1 by Kt minus tau n times P1 by Kt equal to 0, or simply N1 by P1 is tau n by tau p. This is what we have obtained for this whole thing. Now N1 is simply Ni Gt, okay, Gt exponential of Et minus Ei by Kt divided by, this has been divided by Ni by Gt exponential of Ei minus Et by Kt. This has to be equal to tau and tau. Okay, and Ni and Ni will go, and this will be simply equal to Gt square exponential of this will be Et. If I take Et to be equal to this thing, so it will be plus 2 times Et minus Ei by Kt. This is equal to tau n by tau. Okay, this is the expression what we have got. Okay, but we have been given in question, what we have been given, we have been told that the degeneracy factor is 1 and electron and hole both have equal carrier lifetimes. So it is simply, if we take the ln, ln of this expression, it will simply be Et 2Et minus Ei by Kt is equal to ln of tau n by tau p, or it is simply Et is equal to Ei plus Kt 2 ln of tau n by tau p. Why I have written the general form for this is because sometimes we can have this tau n and tau p not equal, which is actually the case. They are not equal, but in this problem we have been given that they are equal. So as a result, this will simply be Et is Ei plus Kt by 2 ln of 1, since tau n equal to tau p. So this is simply Et equal to Ei. So it is simply this Ei is approximately located at the middle of the band gap. So it is the middle of band. So the so what we can say from this, we can select option B, and we can say that for the maximum recombination, for the maximum recombination, the trap states uh, will produce the efficient recombination when it is near the middle of the band gap. Okay, when it's close to the middle of the band gap. Now moving to another problem, which says that we have the minority carrier lifetime. The minority carrier lifetime of electrons in a semiconductor is 9 into 10 to the power of minus 12 second. Okay, this is the minority carrier lifetime, and we have been given is, as we have been given the carrier mobility, which is the electron mobility, which is 350 centimeter square per volt second. We have been given the thermal voltage, which is 25 millivolts, and from this we need to find the diffusion length of electrons, where the magnitude is of the order of 10 to the power of minus 6 centimeter. So let's first evaluate what we have been given. We have been given the value of this tau n, which is the minority carrier lifetime, which is 9 into 10 to the power of minus 12. Mu n is simply 350 centimeter square per volt second. So, and also the thermal voltage is 25 millivolts. So we have to use the Einstein's relation. Sorry, I guess I wrote previously over here as well. Okay, so let me rectify this. I had used wrong spelling. Okay, I had done a mistake. I have used E over here as well. So we are using this Einstein's relation, which says that dN by mu n is simply kT by Q. kT by Q is the thermal voltage, which is Vt. Okay, the diffusion length is simply ln, and it is given by dn tau. This dn is the diffusion coefficient and tau n is the carrier lifetime, minority carrier lifetime. dn we found out is simply mu n times vt. From here, dn is simply mu n times vt, and it is simply dn times mu n times vt into tau. Mobility is 350 centimeters square per volt second. Vt is 25 into 10 to the power of minus 3 since it's millivolt, and the lifetime is 9 into 10 to the power of minus 2. Okay, so let's solve for this. Three is root of 7875, root of 7875, which is 88.7 into 10 to the power of minus 7. So it is coming out to be equal to 8.87 into 10 to the power of minus 6 centimeter. So it is approximately equal to 8.9 into 10 to the power of minus 6 centimeter. So the option A is the correct option to go. Now moving to another problem, which says that uh, we have been given the energy band diagram in the figure, and we have been given the electron concentration. Okay, and we have to find the electron current density at x equal to 0. Okay, what do we need? We need the drift and diffusion current components. Okay, so the what we can do is simply now we need to find the drift and the diffusion at x equal to 0. Okay, at x equal to 0. So since you can see that there is a slope, sorry, let me write like this. Slope in energy band diagram. Slope in energy band diagram, what is it indicative of? Or it is simply indicative of what? Electric field. Okay, whenever you see a slope in the energy band diagram, let's be clear, energy, what is the difference between energy band structure and the energy band diagram? Energy band diagram is the relation of energy with respect to the real axis, real coordinate system x. In here, for example, we are having the relation E versus x, where x is the real coordinate system in the real world. Okay, and energy band structure is simply the energy versus k relation, where k is the uh, reciprocal, in the reciprocal space. Okay, it is the k and x are related to, you can say, like frequency and time are related to themselves. Similar is the case with the x and the k. X is for example, x is the real space coordinate, and 1 by x will be the reciprocal space coordinate. Okay, so the difference between two is that one is in the real space and one is in the reciprocal space. Energy band structure will be in the reciprocal space, and energy band diagram is in the real coordinate system space. Okay, so that's the main difference between the two. So what we can do now is we can clearly say that this figure over here, it is having a slope in the energy band diagram, and this indicates the the system which is given in this problem. It is having the electric field in it. Okay, it's having some built-in electric field, or it can be external electric field as well. But since this concentration gradient is over there, it will be most probably due to the concentration gradient itself, we will be having this built-in field that is being developed. So the electric field is simply 1 by q. Let's take the conduction band energy as a reference, dEc by dx, and it is simply over here, it has been given to be equal to 0.1 electron volt. Okay, we have got this value to be equal to 0.1 electron volt per centimeter. Okay, now what we can do, since it is electron volt, it is divided by electron, and electron, it is simply, we have taken q as well. Okay, it will be minus 0.1 volt per centimeter. Since q and q both are the it is one and the same thing, what we can see. So you can say the total current density is simply the sum of two current densities. One is the drift current and other is the diffusion current. So drift current component is simply given by q mu n and e, and diffusion current component is given by simply q dn d and the derivative of the concentration, that is the concentration gradient. Now n of x is simply 10 to the power of 15 exponential of qz. Z is constant, by the way, it is not the coordinate z. Okay, x is the coordinate. We are dealing in one dimensional problem. Okay, kt, where z is equal to 0.1 volt per centimeter, I guess. Okay, it is 0.1 volt per centimeter. So simply electric field times, so the total current density will simply be q times n is simply 10 to the power of 15 exponential of qzx by kt, qzx by kt, mu n, and field is minus 0.1 volt per centimeter, plus q dn by dx. Okay, we have to do the derivative of this thing, which is 10 to the power of 15 exponential of x by, okay, so it is simply minus q, or let's not write minus q, let's take q outside, q times minus 10 to the power 14 into zero point 0.1 exponential of q z x t times mu n plus dn d times 10 to the power of 15, and it is simply qz by kt times exponential of a z x. Okay, this is what we got. So it is simply z is equal to z is equal to 0.1 volt per centimeter. Z is equal to 0.1 volt per centimeter. So what we get is J total is simply equal to Q times minus 10 to the power of 14 exponential of 0.1 Qx by Kt times mu n plus 10 to the power of 14 dn. This is 0.1 Kt q exponential of zx. Okay, so if I take 10 to the power of 14 outside, it is 10 to the power of 14. It is mu n times exponential of minus times exponential of 0.1 qx by kt plus 10 to the power 14 I have taken common dn kt by q exponential of x by kt. But we know dn by mu n is simply kt by q, or dn is simply mu n times kt by q. So if I use this in equation 1, using dn equal to kt by q mu n, we can clearly see that this whole thing is simply q times 10 to the power of 14 exponential of qzx by kt times minus mu n plus mu n kt by q times q by kt. What we have done, we have replaced dn in this expression. So this will go with this thing and this will be 0. So as a result of this thing, we will be having J total equal to 0 ampere per centimeter. So we will be having 0 current density inside this semiconductor material. So since none of the option is matching with our solution, we will select option D, because the concentration gradient has resulted in the inbuilt field, and as a result of this thing we are having the zero uh, zero total current density due to the electrons. Okay, so let's now move to another concept, which you must have gone through the lectures which professor is teaching to you. And in this lecture, in this week's lecture, and in this week's assignment, there was this metal semiconductor junction that professor was teaching, and all the assignment questions in today's week that you need to solve in this week's problems is associated with this metal semiconductor junction itself. So I will just give an overview, and my all my notes, or what I can say, what I am going to teach is from this book, which is known by the name of this Physics of Semiconductor Devices by SMZ. Okay, so I will just touch a bit, or a bit, what you can say, a bit of this metal semiconductor junction. We will just go through the can say first few pages of the introduction of this book, and what you can use that knowledge, and you can try to use that knowledge to solve the assignment problems and impart it in your course itself. So you must have seen that whenever we have this metal and semiconductor, every time whenever, for example, I am having a semiconductor, I need to make a contact to this semiconductor in order to communicate to the external world. Because, for example, whenever I am having a device like MOSFET, for example, I need to have source contact, I need to have drain contact, I need to have gate contact, I need to have body contact. Okay, these are the main four terminals that we usually have in our four terminal MOSFET. Okay, so this four terminal MOSFET, considering a single gate device, for example, we will be needing a metallic gate. We will be having the need of the metallic source. Okay, so that there is efficient transmission of the carriers from the source. Okay, and we will be needing this efficient collector junction, which is efficient collector material. For example, at the drain, we will be needing this metal, which is able to properly or efficiently obtain or collect the carriers. Okay, so this metal semiconductor junction is really important for the application in terms of the what you can say, in terms of the contact study itself. Okay, so we can say that whenever, for example, a metal will make a contact with the semiconductor, we will be having this Fermi level balancing, because whenever we are in thermal equilibrium, the Fermi level has to be consistent or constant throughout the whole system. Okay, for example, if I am contacting the metal with the semiconductor, now they will equilibrate in such a way that the whole system will now have a common Fermi level at thermal equilibrium. So what we can say, well, let me read out one statement from the book itself. It says that when the metal makes contact with semiconductor, a barrier is formed at the metal semiconductor interface. This barrier is formed. What is the reason for this? If I consider the interfaces to be free from the defects and the impurities, if I am considering the ideal interfaces, this defect will mainly arise from the difference of the metal work function and the semiconductor electron affinity, and the, we can say, the semiconductor basically has the electron affinity, which is the main governing factor. And also we know that the Fermi level of the semiconductor can be changed by doping the material. So as a result, the semiconductor material has variable work function, which depends on the doping, how much we are doping the material. Okay, but in case of this electron affinity, which is the electron affinity is simply the distance between the vacuum level and the conduction band edge. So this will never change for any semiconductor. Okay, this will always remain constant. So as a result, electron affinity is unique for every semiconductor. And they and for metal has the work function, which is the difference between the Fermi level of the metal and the vacuum level. So this barrier, what I talked previously, that whenever a metal makes a contact with this semiconductor, we will be having a barrier formation, and this barrier is mostly responsible for the carrier transport, because now it will be modulating the movement of the carriers from, let's say, from the metal to the semiconductor. So so if we consider the, for example, if I consider the vacuum level, for example, if I am considering this is the vacuum level, let's say this is the vacuum level, and this is my metal. Okay, my metal, and my metal will be having some work function which is given by Q phi m. This is the metal work function. Okay, and the semiconductor, let's say they are separated, they are far away from each other. Okay, when they are far away from each other, and let's say this is my semiconductor, this is EC, this is the electron affinity. Okay, this is the semiconductor electron affinity. Now the Fermi, let me consider the n-type material. Okay, the Fermi will be close to the conduction band, and the difference between the Fermi level and the conduction band, that is denoted by Q phi n, and the valence band will be located somewhere below. So this is the case. This is the for example the case when the metal work function is greater than the semiconductor work function. Okay, so basically the phi m is greater than phi s. Okay, so this is ideal case where both metal and semiconductor are far away. Okay, so this was the ideal case when both metal and semiconductor was far away. Now if we connect these two somehow, for example, somehow is connecting by the wire or by bringing them close to each other. Okay, so there will be this flow of electrons, because this Fermi level of the on the semiconductor side, if this is my semiconductor side, this is my metal, the Fermi level is above the metal work function, and as a result of this thing, this metal Fermi level, since it is below the Fermi level of the semiconductor, we will be having the charge flow from the semiconductor to the metal in order to equilibrate the system. Okay, so what does it happen, what will happen is that whenever we try to bring the systems closer to each other, for example, if I am bringing this system, this is my, let us say, Q phi m, and this is our, for example, now this gap has been reduced, this gap, this is the gap, now we have reduced this gap. As a result of this thing, we will be having this system trying to equilibrate. Okay, and they there will be net accumulation of the electrons on the metal side, since this metal is itself having a lot of electrons. We say that metal is a sea of electrons, so we won't show the band bending in here, but in the reality what would happen, there will be a little of band bending in the metal itself, a little band bending. So this is the band bending which is happening due to the system trying to equilibrate itself. Okay, Similar band bending will happen in the valence band as well. This is when we have reduced this delta, okay, this gap. Now if we try to keep on reducing this gap, this semiconductor will itself try to push the carriers more and more from the semiconductor side into the metal side, and a point will reach when we will be having a metal simply in contact with this semiconductor, and this thing which we have drawn over here, EF, and this is the barrier to my carriers, this Q phi B naught, and this will be the barrier to my carriers, PV, this is PC. So what we have done over here is that we have brought the metal and the semiconductor close to each other that much. Now all the carriers or the carriers of the semiconductor have moved, a lot of semiconductor electrons have moved from the semiconductor side to the metal side, and as a result of this thing we will be having the depletion of the carriers, which you see over here, the depletion of the carriers on the semiconductor side, and there will be this accumulation of the electrons on the metal side. So this thing over here, this thing which is the difference between this edge and the conduction band edge in the bulk, is simply the built-in potential, which is Q phi Bi, and this total thing where we are having this band bending is known by the depletion bit, okay, is known by the depletion, because this region is where the carriers have depleted, and as a result of this thing we will be having now the immobile carriers in this region, immobile ions, not carriers, sorry, immobile ions in this region, and we will be having the free electrons that have moved from this semiconductor side to the metal side, and these both the things, they result in this what we have seen, this potential difference, and this potential difference is known by the name of contact potential. And as I said previously, that these kind of potentials cannot be measured because we will be disturbing the thermal equilibrium, as we are going to, for example, measure for this bias, for this built-in potential, we need to apply some external bias, or we need to have some external current that are being injected into the system. The moment we inject the current or we apply a bias to the system, we will disturb the thermal equilibrium, and as a result of this thing we cannot measure the this contact potentials. So as said, the what we have done, as this gap reduces, the electric field in the gap increases, okay, and what we have negative charge at metal surface, okay, and there will be opposite, equal and opposite charge, which is positive charge on the semiconductor depletion region, okay. So what we can say, and let me continue for this, let me continue on this slide, and there will be positive charge in the depletion region of this semiconductor. Okay, so that's what we have obtained. Now I talked about this metal semiconductor junction when we are having the uh, case of the ideal metal and ideal semiconductor. But in reality, you know that there will be some states which are defect states or interface states will be present in the material, semiconductor material itself, and as a result of that we will not get the ideal Schottky barrier to be equal to the for example this limiting value, the limiting value of this barrier, what we found out, this q, the limiting value of barrier, what we found out was simply q times phi m minus chi. Okay, this will not be the same thing, but because of the gap, for example, whenever we are trying to bring the two materials together, it is not possible in reality. There will be some, let me use another color, there will be some gap. This delta what I have drawn will not be equal to 0. In this case I have drawn this, I have taken this delta to be equal to 0. Okay, but in reality, but this may happen that delta is not equal to 0, and that is the case, okay, in practical applications. And as a result of that thing, we will be having this ideal behavior of this metal semiconductor Schottky junction will not be there. Okay, this barrier is known by the name of Schottky. Okay, this is known as the Schottky barrier. Now there are some conditions on this Schottky barrier. For example, sorry, sorry. Okay, okay. So what it has been found that most of the metals have this phi m ranging between 2 to 6 electron volts, and this metal phi m, this metal phi m is sensitive to contamination of surfaces. Okay, now let us see what happens when we have this different biases uh, which we apply to this n-type semiconductor. I guess that's not quite a that's a quite advanced thing to show, because the professor must have already told you that thing. So let me draw the p-type semiconductor. Okay, for p-type semiconductor, the Schottky barrier will simply look like the opposite to what we have drawn. If this is the EC, okay, this will flatten out. Okay, this is the EF. Okay, this will be the E, and this will be my barrier Q phi B dash. Let me write it down to be equal to Q phi B dash, and this will be my built-in potential. Okay, this will be the Schottky contact in case of the p-type. Okay, so what we have seen is that the Schottky contact largely depends on the uh, interface states. Okay, it can be largely influenced by the interface states, and we have seen that the Schottky barrier for p-type, it is that the holes now have now they will see a barrier when they are going from the metal to the semiconductor. And similarly, in the metal Schottky contact, what we saw that is that whenever we are having the metal which is being brought close to the semiconductor, there will be some finite infinitesimally small gap, and that will be, let's say, delta equal to zero point 0.1 angstrom, zero point 0.2 angstrom, let's say, that will be of the atomic scale, this gap. And that gap will also impact the metal semiconductor barrier. And there is also, because of these interface traps and interface states, there is also the Fermi level pinning that is happening. Because we clearly see that, for example, whenever we study this metal semiconductor junction, we say that the uh, this barrier ideally will be simply phi ms, okay, phi m minus phi s. But in reality, the interface states, whenever they come into the picture, they pin the Fermi level, okay, at some particular value, and as a result of that thing, we are not able to get the ideal Schottky barrier. So I guess that is it from my side for this Schottky barrier, you can say, introduction. Because since the assignment deadline will be this week for the Schottky barrier, and we will be solving the Schottky barrier problems in the next week only. And this I hope this introduction, just although this is just the introduction which the professor also taught, and I hope this introduction will help you to gain some insights, and you will be having this thing in mind that this metal and semiconductor, it is not always that they will be having zero gap between them. There will be some small gap present between them in reality, what I am talking about. And also there will be some interface states at the metal semiconductor junction that will pin this Fermi level, okay, that will not allow this Fermi level to go ideally, okay. So as a result of that thing, this metal semiconductor junction cannot be, in real scenario, cannot be predicted by this ideal, what is known by the name of, this is known by the name of Mott Schottky barrier, okay, Mott barrier, okay, Mott barrier, it is known by the name of Mott basically was the one who who devised a proper name for this metal semiconductor contact, and it was named by his name. Therefore, this ideal barrier, it was named by the name of Mott barrier. And you can see in this case, let me briefly show that we will be having, there will be five kind of transport mechanisms of for the carriers. But let me just give you one small insight. There are two transport mechanisms that you should be knowing that are happening. One is this, which is the thermionic emission. This is known by the name of the thermionic emission, and this is the tunneling process, okay. There can be two processes happening, okay, although there will be recombination, there will be diffusion also. But I am just for the let's say, for making it a bit easier, I am just saying that the carriers can just go over this barrier and move to the semiconductor. This is known by the name of the thermionic emission. And or these carriers, they can tunnel through this barrier, okay, they can simply tunnel through this barrier. Now this tunneling will depend on this barrier height and as well as the thickness of this barrier. So we can reduce the thickness of this barrier, reduce the thickness of this barrier by doping, okay. We can dope this region, and we can make this barrier, the Schottky barrier, to be thin and thinner and thinner. And as a result of that thing, we will be having the high tunneling current. So these two mechanisms, one is the thermionic emission and other is the tunneling mechanism. They can be considered as the governing transfer mechanism. Although recombination and diffusion will also be there, but let's not go into the details of those. So I guess that's all what we need to know about this metal semiconductor junction. So if you have any questions, you can unmute yourself and you can ask. Or if there are no questions, we can end the session. Okay, please unmute yourself. Yes, you can unmute yourself, please. So I guess there are no questions. So if there are no questions, we can end the session. Thank you for joining the session.